Chances are you've all been having problems with question 19. Yeah, we're gonna show you how to do that. But first, before I show you anything, I want to teach you this. Does anyone know that? Do I need to explain that? What's this topic or the whole thing that we'll be teaching is, I call it the fundamental Loopdeloop, but it's called integration by parts twice. Or at least that's what they've been referred to as. Judging by nobody saying anything, I'm going to demonstrate why this is true. And hopefully it'll make sense. Does this make sense so far? Can you read it in the back? Does anyone understand why? Or not understand why? We take the derivative of the natural log, we put it in the denominator, and then through the chain rule we have to take each individual one and come up with this. And then we'll come up with this beautiful piece of math.
Is that one secant x?
Where? Okay.
To the right. One secant x.
That's absolutely.
Oh, okay.
Does that make sense? Yeah. Good. Beautiful. Alright. Wait, what? Do you want to the other part or should I go to the just kidding.
Yeah, alright, so yeah, I'll go. Okay, sorry. So just remember that for now.
This will come back.
Yeah, this has nothing to do with that, but I'm just going to basically show you guys a strategy that we call the fundamental loop-de-loop. It's basically just taking the interval twice and then solving for the original. Doing integration by parts twice and then solving for the original. So an example of that would be the integral of e to the x cosine x. So to set up the integration by parts, you remember Deontay and trig comes before exponential function, so make u equal to cosine x and dv e to the x dx. Right? So then when you take the derivative, you get negative sine x dx, and when you take the interval, you get e to the x. So far, so good. And then you do the ultraviolet supervoodoo, so you get the x cosine x, and that's, you can carry this negative sign out to here, and you get
Sense?
So when I was doing the homework problem, I realized it's just gonna go back in a circle to this. So I gave up, but then I talked to my old calculus teacher, and he told me just to do integration by parts again, and then just stare at it. That was his theory. So I did it again. And we'll just go like this for now, so I don't have to make it over. And so you stared at it, and then I realized that this is the same as what you started with. So if you rewrite it as e to x cosine x dx equals e to x like that, you can subtract this. I mean, you can add this whole thing to both sides and get now to solve for the integral of e to the x cosine x dx, you just divide both sides by 2. And then this is your answer. Oh, hold on. Don't forget the c. And an example of something that can go wrong while you're doing this is, let's just say that when you do the integration by parts again, you decide to make u equal to e to the x and dv equal to sine x dx. I'm just going to show you an example of that over here. So we're just going to start with the, after you do it the first time, so we're going to start with, okay. So let's just say you want it to be a rebel and not follow the rules of the algorithm, and you make a u equal to e to the x. So then you do the same thing over. And then if you simplify it, yeah. And you see that you get something similar, but if you wish to subtract this to the other side, you get 0, and then these two cancel, and so you end up with 0 equals 0. And you're very confused. So this is what happened to me on one of the problems, I think it was 19. And my tip to you guys is just to, don't go back and try it all over again. Just go back to when you had this and do it, and switch your U and DV. So instead of saying U equals e to the x and DV equals sine x, do U equals sine x and DV equals e to the x, and try it again. And hopefully that helps you guys get the right answer or not. Well, I mean, this is still correct, but it's not very useful. So now I'm going to pass it over to CJ. So,
All right.
you guys.
And now, the monster. Last week, we learned how we can do the integration of tangents and secants such that tangent has an odd power, or secant has an even power, or both. But in this situation, in which we have tangent to the 0, which is just pretend it's there if it makes you feel better. Does anyone know how to do this monstrosity? Notice that everyone waited until just the same moment to start talking, so I didn't get any of that.
Fundamental Loopdeloop.
Yes, fundamental Loopdeloop. There are two routes we can take first. We can either convert a secant squared into the tangents, or we can start with the ultraviolet super voodoo. Does anyone have a preference as to where to start from?
Do both.
Do both. Okay, which one am I doing? You do first.
Do super voodoo.
This will become relevant soon. I'm just going to do the ultraviolet super voodoo, if that's alright. U equals secant, and dV equal to secant squared. So V becomes tangent, and U becomes secant tangent.
CJ, I have a question. Why did you break it up that way in the first place? Why did you make your U be one secant and dV be two secants?
Because before you actually do the problem and find out that it becomes a disgrace, if you were to thank you. If you were to, this way looks very nice to me. Like, before I know that it becomes something bad, it looks nice to have all just the simple one and then its derivative of each kind. It seems a lot simpler because the derivative of this would be 2 secant squared tangent, and nobody wants to deal with that, even though we're going to have to anyway, but we don't know that yet. So, we'll find that this is secant tangent minus secant x tangent squared of x. Now we could do what he did and mess up and get 0 equals 0. We would have a correct answer, but we're not going to do that because we can turn tangent squared into secants and it would come out a lot nicer. So I'm going to tangent squared, we tan for 1 second. And I'm just going to put this on the other side so we don't have to write it all out again. And I'm only going to bring this down. We'll have secant cubed minus, and this would be a minus, but we make it a plus because it's minus a plus, and be the integral of secant. That's where this becomes relevant. But here we have this again. Just like how we had this again here. And I'm not going to make the McDonald's joke again. Doesn't seem right. So,
Now I wanna know it though.
You can't just drop something like that.
alright, you have this, but that's also on the other side. But now is not the time to quit and go work at McDonald's. I'm gonna replace this with the answer we have over there. Was it funny twice?
Yes.
Anyone solve it from here? Did I write too small? Is my handwriting bad?
It's excellent.
It's excellent?
Yeah.
Thank you. I don't try my best. Add that to both sides. You put a 2 here, get rid of this. And I think it looks easy from here, especially with this right here. Put this over 2, erase this, add, what's the one for? Arbitrary constant. Does that make sense to anyone? Should I demonstrate it again? Yeah.
Can you explain how you went, like, I get the secant cube, but why is there another integral of
Yeah.
secant x? Yeah, that.
Oh yeah, okay, I'm gonna put it over here then. When we turn tangent squared into this, what we should come up with looks like this.
Oh,
You see from here? Does anyone else want me to finish that?
You just said right the rest.
Okay.
You just said right the secant x and x all the time.
And then I split this into 2 separate integrals. And that's this.
But you have to remember that there's this negative sign right here. So you have to distribute the negative sign here.
Negative and this. Look at that. Any questions? A no would suffice.
No.
Well, that's good. That means I did it right.
So then how about these general ones? If people are comfortable with that one, then tell us how we approach this general case of even tangents and odd secants.
Ah, yes, yes.
What do we do?
Alright, let's say we have secant cubed, but instead of making tangent 0, let's make it tangent of 4,000. Now you should start working at McDonald's. Does anyone want to take a guess as to how you do this? Actually, this one isn't bad.
Okay, so you would just convert all the tangents to secants, and since you're taking 2 at a time, using the tan for 1 second formula, get there, you would end up with, you'd get rid of all the tangents and end up with an odd number of secants. And you do something like this, but it would take much longer.
I would convert the secants into tangents.
Oh, never mind.
Because if you make the secants into tangents, you'd probably only have, you'd come up with secant times tangent to the 4,002 minus secant to the tangent of the 4,000, I believe. Yeah. But if you did the tangents, you'd have to go down ultimately 2,000 layers of tangents before you finally had 2 to the 2,000th powers integrals, all of which are secant of different values. It would be hell. And I wouldn't recommend doing that. I'd recommend taking the sequent approach. I'd just say, whichever one's lower, you should work with that one. And one of them will always be lower because this one has to be odd and this one has to be even to get that. Any questions? Should I demonstrate? Yeah? Okay. Analysis. It looks worse, but these two are easier than this one. So while there are two of them, it's easier to do. If that makes sense. And that's the point at which you'd start doing the ultraviolet supervision. And grind yourself to sleep at night. Any questions?
The point here is that running it 2,000 times is really not a big deal because this is something you would put on a computer.
Yes.
And so if you have an algorithm that takes 2,000 steps, that's fine. The computer will do 2,000 steps in the blink of an eye. But you have to know something that'll work. So you have to have a method to give the computer. So as long as you have a method that works, it doesn't really matter how many steps it takes.
So ultimately, if you get a question as ugly as this, or let's say this is 31, no one wants to do that. If you get a question like this, you know how to do it, but just ask the computer, right? Yeah, that's what I do. I could spend all of Saturday night at home, but I have a computer.
But what I don't want the computer to be a mysterious black box.
You know what to do, right? Yeah.
Yeah.
You just don't want to because you have plans.
So how would you do secant to the fifth, CJ?
You all know this?
Yeah.
What I would do, actually, I'd go straight to the ultraviolet superglue. Okay, no. You would go straight to tangent squared. We all just learned how to do this. From there you could, well, there are a lot of ways to approach it. Give it a try. we've already attacked right here. So we can do that again. And this one is a lot easier than this one. So that's sub 1, it's that sub 2. And then we have and from here, how would we do this one? I'm sure there's some ultraviolet super voodoo somewhere going on there.
I would have started with parts right away, and
Yeah, that probably would have been best.
but basically, it's going to work out similar to what you did for secant cube. So yes, yeah. So I'm not sure it's worth taking the time to drag everybody else through that.
And the that's.
Sorry?
And the that's.
Yeah, the that's are going to come in
That's
as well. So let me give other people a chance to talk. Go ahead, Ruby.
I know this sounds like stupid, but could you convert it to 1 over cosine to the 5th if you don't want to do secant?
Well, you could. If you have a question like that, the answer is always you can. But, where would you go from there?
Do cosine squared.
That sounds nasty.
That sounds nasty too.
Well, yeah, but with this method, everything will be in the denominator. And then finally, we'll have to do the u to the negative something of power integral. And it's not. I'd recommend this as long as you can, because if you do the ultraviolet super voodoo first, it should come out as a bunch of secants. You want to do that?
Yeah, let's do that.
Alright.
Let's start that.
So for help.
Just do the first step of parts. Let's not drag everybody all the way through
Of
it.
course. U, UV. I'm tempted to make the dv secant squared so I can come up with a nice tangent here. Alright, that's what I thought. I just don't like what happens with the u in that case. Because I'm gonna need more room to write. Breeze to come up with tangent secant cubed minus the integral of secant cubed tangent squared, which is right here, but we're not there yet because when you go the extra path, you'll get that as I erased.
He's got a mistake there. Help him find it.
Where? Someone found it? I still can't find it.
How is your u secant cube and your dv secant squared? Shouldn't your dv be?
Isn't free sequence where it is?
Is it this? Oh wait, is it this?
No, it was more. It's more serious than that.
Alright.
Justine, what did you say?
It's better than anything we're doing.
It's in the video.
Don't you get
So it's like 3 seconds.
a number up front?
Not quite.
Square of x times the derivative of secant x, which is tangent x, and another secant x, which is cubed.
View.
Oh, sorry. I was squinting here. I didn't realize that you had 3 secant cubed. I thought it was 3 secant. I thought you had 3 secant squared. So I take back what I said about the mistake.
I am flawless.
Well, I'll just say the mistake was the dx. So good job catching that.
And we had this and this, and I'm not gonna go through them.
So what would you do with that?
This,
Yeah.
I would sigh heavily.
Probably should just convert tangents.
Oh yeah, I'd convert the tangents to secants, and then you should get the fundamental loop.
Nice. Nice.
Flawless.
Can't be changed, DJ. Can't be changed.
Any questions? Any statements that are not questions? Any testimonials?
Actually, I learned this method called the ladder method. It's kind of like the fundamental loop-de-loop, but you do it all in one step instead of, like, I don't necessarily know how to explain it besides showing it, like using the first one. Does anyone mind if I show it?
Go for it. So I'm wondering, this might be is this the same thing as what some people call tabular integration?
I don't know.
Okay, well, go for it.
I learned this, like, not too long ago.
Can I erase that?
Yeah, go through it.
No. So the original equation was just. So it's e to the x cosine x dx, and then I had my u just equal just cosine x, and dv just equal e to the x. And when I went the first time down, I noticed that nothing really is gonna happen. This isn't gonna get you anywhere, and so I just went again. And then I noticed it fundamental loop-de-loop kind of. It just kind of looped around. I don't know the proper notation for that.
Technically, yeah.
Is it d squared u? Sorry.
It's okay.
And I noticed it kind of just loops back around. And the way I learned this was you can kind of go down like a ladder, where this is first one's positive and then negative and then positive, and you can keep going for how many different ways loop-de-loops you need to go. Crazy roller coaster. And then you just, it's kind of like UV. It's UV minus DUV minus. You just multiply, and that's just your sign for each one of them. So it's just e to the x cosine x minus a negative sine x e to the x. So just giant positive. And then you have plus a minus cosine x e to the x. So that just makes giant whatever. That last one's always an integral. And then then it usually ends up being the same thing. You just need to wait for it to flip back around to its regular side, or whatever. Yeah, everyone understands what I'm saying, right? Yes. Does everyone get it? Yeah, I know what I'm doing. And then you just go on to this part, where you bring it over and then multiply it out. I just did it all in one step instead of doing it in 2 steps. That's just how I learned how to do that. Any comments on that one?
I think it's cool.
Thanks.
Are we ready to let these guys off the hook? All right, thanks, guys. So, at least in theory now, everybody knows how to do all the problems, including number 19, which you can use this fundamental Loopdeloop to solve. So I'm going to let you guys get back in your groups. Like I said, you should be able to do all the problems that are due today, and the first 6 problems that are due next week. If you have time to start working on those, you know how to do them. Everything after that is trig substitution, which unless you learned it from somebody